Okay, let's go ahead and start. Does anybody have any questions before I begin? The game plan today is to complete this topic, and then we're going to move on to the next topic, which is electrochemistry. Okay? So if you guys remember, last time at the end of class, we looked at the common ion effect. And simply put, common ion effect is the application of Le Chatelier's principle. And we said, when you take an equilibrium and add a common ion that is common to that equilibrium, the way the system responds is called the common ion effect. When we dealt with acids and bases, the common ion effect affected the pH. So you could see how we changed the hydronium ion concentration or the hydroxide ion concentration, and how that affected the pH of that solution. When we deal with solubility product, our concern now is looking at solubility. So we look at how the common ion effect affects solubility. So at the end of class last time, I asked you to take a look at this problem, and I asked you to try this out at home. And so let's very quickly go through the solution of this problem. So if you know your acid-base chemistry, then this problem should be pretty straightforward, because what we have is we have silver chloride, and we're adding sodium chloride in addition to that. So we know that we're adding sodium chloride, therefore it is a common ion effect. Okay, so if we take sodium chloride is a soluble salt, and we know the instant you dissolve it, that is going to give me Na plus Cl minus. And because our volume does not change, the total volume does not change, we know that the concentration of sodium ions would be 0.1 molar, and the concentration of the sodium chloride ions would be 0.1 molar. Because it dissociates completely. If you start with 0.1 molar NaCl, when it dissociates, we know that this is going to be the concentration of the cations and the anions. Now this is the common ion. Chloride is the common ion. The equilibrium that we're interested in looking at, of course, is AgCl, and this establishes this equilibrium. And we know that Ksp equals 1.6 times 10 to the negative 10. And so to begin with, we have sodium chloride contributing chloride ions. And so now we need to look at the initial concentrations. And since this is a precipitate, we don't need to concern ourselves with the concentration of AgCl. We have 0 to begin with. But over here, because we started with sodium chloride as well, we know that the concentration of the chloride ion would be 0.1. Now if we're looking at the change, we know that the reaction has to take place in the forward direction. Therefore, this would be plus X, this would be plus X. We're not really concerned about the reactant because it doesn't appear in the equilibrium expression. Okay? And so at equilibrium, we know this would be X, and this would be 1 plus X. Okay? So now we need to solve for X. So we know that Ksp is 1.6 times 10 to the negative 10. And we know that equals the silver ion concentration times the chloride ion concentration, which is X times 0.100 plus X. Now, at this point, we ask ourselves, can we make an approximation? Remember, this is 10 to the negative 10. So that's a really small number. So we know that X has to be really small compared to this number. And therefore, we can make an approximation. And our approximation is going to be that X is going to be so small compared to 0.1 that we can actually neglect it. Okay? So now we can go back and we can say now that 1.6 times 10 to the negative 10 equals X times 0.1. Therefore, X equals 1.6 times 10 to the negative 9 moles per liter. Okay? And remember, what we're asked to calculate is we're asked to calculate solubility. Okay? And so once I've calculated X, I would quickly check validity. And you can see that the validity comes out to be a really small number. It comes out to something like 10 to the negative 6%. So you know that our approximation is pretty good. Okay? And now we can say that solubility equals X, which is 1.6 times 10 to the negative 9 molar. Now, in this case, they haven't asked us to calculate gram solubility. Okay, and so if they don't ask you, you don't need to calculate it. But if you did calculate gram solubility, you would take the molar solubility, which is 1.6 times 10 to the negative 9 moles per liter. Now we're going to convert moles to grams. So that means I need to multiply by the molar mass, which is 143.3 grams of silver chloride per mole. And so if you calculate gram solubility, that comes out to be 2.3 times 10 to the negative 7 grams per liter silver chloride. All right, so its molar solubility would be that. Its gram solubility would be that. Now, one of the things that we predicted was the effect of adding a common ion is that the solubility decreases, because we know when you add a common ion like chloride, now we know the system is going to respond by moving towards the reverse direction or shifting to the left, and so what happens is solubility decreases. Now we can actually check that, because remember when we first started looking at solubility, if you remember, we calculated the solubility for silver chloride. So if I didn't have a common ion, then this would be XX, and therefore it would be X squared, and you can solve for it, and therefore your molar solubility comes out to be 1.3 times 10 to the negative 5. So in the absence of adding the common ion, our solubility is 1.3 times 10 to the negative 5. If you add sodium chloride, now it becomes 1.6 times 10 to the negative 9. Can you see the two numbers? All right? So if you were to put this side by side, you can see that the solubility is, you can compare these two numbers. If you want to compare gram solubility, you can compare these two numbers. Now, overall, if you look at it, the difference is approximately 10,000. Can you see the difference between the two numbers is approximately 10,000, or 4 orders of magnitude? Do you see that? So the addition of sodium chloride actually decreases the solubility. You can see that approximately it decreases solubility from this number to this number, and there's about a 10,000-fold decrease in solubility. Do you see that? And that is the effect of adding the common ion. So you can clearly see that if you add the common ion, now the solubility has gone down. All right? And that is an illustration of the common ion effect, the effect of adding a common ion to that system. Okay? Now the last thing, did anybody have any questions? Now the last topic that we're going to look at here is we're going to look at the effects of pH on solubility. Okay, so the last topic that we're going to look at is the effects of pH on solubility. So, effect of pH on solubility. So, pH can affect the solubility of a salt. So it turns out it depends. All right, sometimes it does, sometimes it doesn't, and we're going to look at examples where the pH affects solubility. The first class of compounds we're going to look at is solubility of metal hydroxides. All right, now it turns out the solubility of metal hydroxides are affected by pH. All right, so the solubility of metal hydroxides are affected by pH. So let's take an example. A metal hydroxide is one that has metal cations and hydroxide ions as the anions. And so if you take something like zinc hydroxide, this is an insoluble salt. And remember we said, if you're not quite sure, you can look at solubility rules, and you know that the only hydroxides that do dissolve are group 1 metal ions and ammonium ions. All right? Most of the hydroxides are insoluble. So if you take zinc hydroxide, and you will establish this equilibrium where you have zinc 2 plus aqueous plus 2 OH minus aqueous, and this has a KSP of 1.2 times 10 to the negative 17. If you take another hydroxide like iron hydroxide, now this will establish an equilibrium. See, there are 3 hydroxides attached to this ion. So what is the oxidation state, or what is the charge on that ion? 3 plus, all right? So this would be ion 3 plus. And we have 3 hydroxides. Remember, your equations have to be balanced. So the 3 hydroxides will balance the charge on the 3 ions. And the KSP for this is 4.1 times 10 to the negative 38. So you can see both of these KSP values are really, really small. And that means these are insoluble salts. All right? Now, if you take both of these, you can see that one of the ions that you form is hydroxide. All right? So let's look at its effect. What happens if you change the pH of the solution? Okay? So let's say pH is greater than 7. In other words, we have basic solution. Now, if you have basic solution, remember, what does it mean when your solution is basic? That means it's got hydroxide ions, all right? Or pH is greater than 7 means it's got hydroxide ions. So can you see the moment you had hydroxide ions, now you have a common ion effect. What happens to solubility? Solubility decreases, all right? So there are OH minus ions. Solubility of the salt decreases. All right? Now, what if the pH is less than 7? Now you're in acidic solution. So a way to do this is you keep it in a buffer. So let's say you change the pH of that solution so that it's in a buffer that's basic. And what happens is if you place it in a buffer that's basic, solubility is going to go down, okay, compared to neutral solutions. All right? If you're in pure water and compare that with basic solutions, you know the solubility is going to decrease. And as you keep increasing the pH, the solubility will increase even more. Okay? Now, if you put it in acidic solutions, now what happens is that in acidic solution, you're going to have this, let's take zinc hydroxide. So you're going to have zinc hydroxide give it in equilibrium with zinc 2 plus aqueous plus 2 OH minus. But now you're in acidic solution, so this hydroxide will react with the hydronium ion to give you water. Actually, it's going to react, so it's going to give you 2H2O. So what happens is this hydroxide is now essentially being removed from the solution. So can you see that if the hydroxide reacts with hydronium ion, the net result is that the hydroxide is being removed from that solution. So how is this equilibrium going to respond? It's going to move in that direction. So can you see that in acidic solutions, solubility increases? So if I wanted a hydroxide to dissolve, if I make the solution acidic, my metal hydroxide will dissolve. You see that? If I don't want my metal hydroxide to dissolve, if I make the solution basic, then it makes it more insoluble. Do you see that? So in the laboratory, we can actually use pH to control whether we want a metal hydroxide to dissolve or whether we don't want it to dissolve and we want it to precipitate out. Okay, so this is a tool that we take advantage in the laboratory, and by adjusting the pH, you can control the solubility. Now, do you guys remember when you do some experiments in the laboratory, sometimes your substance does not dissolve, all right? And if you're going to do a titration, for example, it means that you have to make your substance dissolve. One way to make it dissolve is to raise the temperature, all right? And so by raising it and heating it up and stirring it up, you can make it dissolve. Another way to make a substance that's very difficult to dissolve is to change the pH, all right? Either to make that solution acidic or basic. It doesn't work for every example, but you can see it works very well for metal hydroxides, okay? Now the second group we're going to look at is, so that's how metal hydroxides are affected by pH. The second class we're going to look at is solubility of metal salts, solubility of metal salts of the conjugate bases of weak acids. All right, so now we're going to look at, we looked at hydroxide as one example. Now we're going to look at examples of conjugate bases of weak acids. So an example of this would be something like CaF2. All right, so if you take calcium fluoride, this is an insoluble substance, and the equilibrium that you would establish would be calcium, giving you 2F minus. And if you take the KSB of that, it's 3.9. So KSB equals 3.9 times 10 to the negative 11. So we know this is an insoluble salt. But if you take the anion, the anion is F minus. And if you take the anion, this is the conjugate base of the weak acid, HF. So it's a weak acid. It's the conjugate base of a weak acid. Therefore, this would be a weak base. You see that? Now, if you take this substance and place it in water, if pH is greater than 7, in other words, if the solution is basic, solubility is not affected. All right, so if you put this in basic solution, what you have is hydroxide, and so what you end up with is just hydroxide and fluoride ions. All right, they're not competing with each other, and so it doesn't affect the pH all that much. It's the solubility of calcium fluoride. It doesn't affect the solubility of calcium fluoride. But if I make the solution acidic, if the pH is less than 7, now it's acidic. What happens is that the F minus is a weak base, and in acidic solution, it's going to combine. Remember, bases and acids in large amounts cannot coexist, and so this will give you HF plus H2O. All right? So you can see that in this case, because you have this reaction taking place, you're essentially removing the fluoride ions from the solution, therefore solubility increases. All right? So if you take the salts that have the conjugate basis of a weak acid, all right, we know that in basic solutions, solubility is unaffected, but in acidic solutions, solubility increases, all right? Because the F minus is the conjugate base of a weak acid with hydronium ion. Can everybody see that between these two, if you have F minus and HF, a weak acid prefers to be HF rather than F minus. Remember, almost 99.9% will want to be HF, and only a small amount will be F minus. So what happens is it'll react with the hydronium ion to give you HF. Okay? Now the third scenario is solubility of metal salts of the conjugate bases of strong acids. All right? And so here you would have something like, so an example would be AgCl. Chloride ion is the conjugate base of a strong acid. All right? So if I take chloride ions, the equilibrium I would establish would be this. And KSB is 1.6 times 10 to the negative 10. All right? Again, if pH is greater than 7, the solution is basic, solubility is not affected. Okay? If you take pH less than 7, in other words, if the solution is acidic, in this case, solubility is not affected. So if you take salts where the anion is the conjugate base of a strong acid, it's not affected by pH, either acidic solution or basic solution. And the reason is that in the case of base, if you have hydroxide, you know that the presence of hydroxide is not going to affect chloride. Okay? But if it's acidic, you know that you have hydronium ion plus Cl minus. Now, because it's a strong acid, and because Cl minus is an extremely weak base, so weak, remember, it can't act as a base in water. So if you take Cl minus, it's not acting as a base in water. Water is a stronger base. Remember, the conjugate base of a strong acid is so weak that it can't act as a base in water. So what happens is that you won't have this reaction taking place. So you won't have this reacting with this to give you HCl plus H2O. That will not take place, all right? Because this is a strong acid, and you can think of it as a strong acid prefers to be dissociated rather than associated. Or you can say that in water, Cl minus can act as a base in water because water is a stronger base. All right? So you can't have this acid-base reaction taking place. All right? And therefore, if you take the conjugate base of a strong acid, it's affected by acidic solutions. Did you guys get that? So now let's take this and apply it in a problem. Okay? So you should be able to predict the solubility effects depending on whether it's a metal hydroxide, whether the salt is the conjugate base of a weak acid, or whether the salt is the conjugate base of a strong acid. Okay? So now we're going to just work that last problem in that worksheet before we move on to the next topic. Okay? And I wanted to kind of point out some things because now your thinking should be much more sophisticated. So I want you to look for small details as well, because now we've looked at this topic for over a month. All right, and you know every aspect of equilibria that takes place in water. Okay, so let's take a look at this one. We're looking at iron hydroxide. So compute the solubility of iron hydroxide in pure water and compare it with a solution buffered at pH 11. Okay, so we're going to first start off by writing the equilibrium expression. So let's start with the part A in pure water. Okay, so if you take iron hydroxide, the equilibrium that you will establish, so this is the solid, is giving you iron 3 plus aqueous plus 3 OH minus aqueous. And we know KSP equals 4 times 10 to the negative 38. It is very, very important that you are able to write the balanced equation for these, okay? So you don't get any brownie points on the exam. If you write the wrong balanced equation, you don't get any points. Is that clear? And so when you write these balanced equations, you have to make sure that you have charge balance. You know what the charge of the cation is. Very often, remember, if it's a transition metal, you turn to the counter ion to figure it out. If it's group 1 or group 2, you can look at the group number and figure out what the oxidation state is. So you know group 1 would be +1. If it's in group 2, it's going to be +2. And then we move on to transition metals. And you move along, and then you go on to heavier metals on the other side. Now, all of those have variable charges, all right? And so if something has a variable charge, then you have to turn to the counter ion to figure out what that charge is going to be. So if you take iron over here, iron is a transition metal. So iron can have a +1 oxidation number or oxidation state. It can have a +2, it can have a +3, it can have +4, it can have +5, it can even go to +6. All right? So if you're going to figure out what the charge on it or what the oxidation state is, then what you need to do is turn to the counter ion. And the counter ion is the hydroxide. There are 3 hydroxides, so you know there are 3 negative charges, so you can figure out what the charge is. Okay? Now, I want you to pay attention to the KSP. It's 10 to the negative 38. That's a really, really small number. All right? So now, because we're dealing with KSPs that are really small, all right? If you look at KW, all of you recognize is KW is 10 to the negative 14. So this number is much, much smaller than KW. And the reason I'm taking this example is that now, because this KSP is so small, that means the amount of iron and hydroxide is going to be really, really small. All right? For a value this small, you cannot ignore the hydroxide ions that come from pure water. What is the concentration of hydroxide ions in pure water? 10 to the negative 7. So now we're looking at an example, now we're in water. In most other examples, when we looked at Kas, remember the Ka values, the smallest value of Ka in water has to be 10 to the negative 14, which is water. Do you understand that? So we always deal with, if it's going to act as an acid in water, that substance will always have a Ka value greater than Kw. Do you see that? And therefore, we always ignored in all those examples, because the concentrations that we started with were high concentrations, we always ignored the contribution that comes from water. In the background, water is always there. All right? In this case, because KSP is enormously small, 10 to the negative 38, all right, way smaller than Kw, you can see that we can no longer ignore the contribution that comes from water. So here, when I look at my initial concentrations, remember this is a solid, it does not appear in the equilibrium expression. Before anything happens, we know that the background water has a concentration of 1 times 10 to the negative 7 molar hydroxide. So the reason I'm taking this example is I'm now pointing out an example where you cannot ignore background water and the contribution that the background water makes, because now the scale at which we're looking at is even less than 10 to the negative 7, okay, because KSP is 10 to the negative 38. So now I can say the change would be, we're not interested in that, this would be plus x. What would that turn out to be? Plus x? Plus 3x. Okay, great. And then at equilibrium, I know this would be x. This would be 1 times 10 to the negative 7 plus 3x. All right? Now, in reality, all of the examples that we took, we should write it like this, but because this 10 to the negative 7 is so small, we don't even consider it, because that number is so small, it doesn't make any difference to the overall calculation. But now here, we're going to say KSP equals 4 times 10 to the negative 38, which equals the concentration of iron 3 plus, take the concentration of hydroxide taken to the power 3, which is x times 1 times 10 to the negative 7 plus 3x, this whole thing taken to the power 3. All right? So you can see that I need to make an approximation. But now, this is where, usually we consider x to be small. All right? Now here, this is an example where x is not small. This x is going to be really small compared to this number. Do you see that? All right? Usually, we always took that approximation. So let's take a look at this. So what we're saying is, even though this number is really, really small, we're going to say that this number is really, really big compared to 3x. And therefore, we're going to say that 1 times 10 to the negative 7 plus 3x will approximate to 1 times 10 to the negative 7. All right? So now we're going to go back and I'm going to say 4 times 10 to the negative 38 equals x times 1 times 10 to the negative 7 taken to the power 3. So x turns out to be, this is 21, so you're, so just do the math. So that will come out to be 10 to the negative 7 moles per liter. All right? They want you to calculate solubility. So solubility would be 4 times 10 to the negative 7 moles per liter. All right? So in this instance, if you're in pure water, that's what the solubility would be. Now in the second part, we're going to make the solution basic now. So now we're going to change the pH of that solution. All right? And what they tell us is that the pH is now 11. So remember, in this equilibrium, it's the hydroxide that we're interested in. All right? Because we want to know now it's iron hydroxide, and the solubility of iron hydroxide is going to be affected by the hydroxide ion concentration. So can everybody see they're giving us pH, but what we really want is pOH, and that will be 3. And if pOH is 3, what is the hydroxide ion concentration? All right? So this goes to 2 decimals, so I'm going to give my number to 2 significant figures. So I've quickly calculated the hydroxide ion concentration. Now I'm going to turn to my equilibrium, which is iron hydroxide. And this is my equilibrium expression. And I know KSP is 4 times 10 to the negative 38. All right? So my initial concentrations would be, so do you understand now, the only difference here is previously we were in pure water where the concentration of hydroxide is 10 to the negative 7. Now we've adjusted the pH so that the pH is now 1 times 10 to, the pH is 11, and at that pH the hydroxide ion concentration will be 1 times 10 to the negative 3. So now when I look at my initial concentrations, once again, I'm not interested in the concentration of the solid. This will be 0. Before anything happens, the concentration of hydroxide would be that. Therefore, my change would be x plus 3x. Therefore, at equilibrium, I know that this would be x. This would be 1 times 10 to the negative 3 plus 3x. All right? Now, once again, we go through the same routine. Okay, so now we're going to say KSB equals concentration of the ion 3 plus times OH minus taken to the power 3, which is x times 1 times 10 to the negative 3 plus 3x, the whole thing taken to the power 3. And we know that since KSB is such a tiny number, we know 3x is going to be really small. So we know that this 10 to the negative 3 has to be much, much bigger than 3x. And therefore, we can say that 1 times 10 to the negative 3 plus 3x should approximate to 1 times 10 to the negative 3. Therefore, KSB equals 4 times 10 to the negative 38 equals x times 1 times 10 to the negative 3 cubed. Okay? So you solve for x, that comes out to be 4 times, this is 9, so this will come out to be 10 to the negative 29 moles per liter. All right? So solubility now becomes 4 times 10 to the 29 moles per liter. All right, so this is an example of the common ion effect. We've changed the pH of the solution. We made the solution basic, so we've increased the hydroxide ion concentration. Therefore, we would expect the solubility to decrease. All right, and let's see where that really does happen. So once again, if you compare the two solubilities, you can see in pure water, it's 10 to the negative 17. Now, if you change the pH to 11, so you make that solution substantially basic, all right, then you can see the solubility goes down to 10 to the negative 29, all right? And therefore, you can see that by making the solution basic, now the solubility has decreased. Is that clear? Now, there are, in your textbook, they talk about how, in the laboratory, this is a very important tool because you can play around with the pH and you can make something dissolve, or you can make something become insoluble, so you can make it precipitate out and you can filter it out and dry it. And so you can play around with solubility and pH to adjust for solubility. Okay? Yes, go ahead.
Exactly how small does the KSP have to be for you to use the hydroxide from water?
Okay, so that's a good question, because where's the cutoff point? Because, you know, when do you need to consider background water and when don't you? All right? That's a tough call. Usually, you know, 10 to the negative 14, a factor of about 100 on either side, you can make that approximation. All right? So if your KSP is of the order of 10 to the negative 14 to 10 to, then you can assume that you can ignore water. The contribution of water is not very great. So 10 to the negative 14 plus or minus a factor of 100. So 10 to the negative 14 to 16 on one side, on the other side, you understand that, okay? Beyond that, you actually have to do it, make the approximation, check for validity, and if your validity doesn't work out, then you know that you made the wrong approximation, okay? Yes?
I've noticed on Wiley Plus that there's some questions about redox.
Yes, that's the next topic. We're going to start that today.
But it's due on Tuesday.
No, I will push those back, okay? Just try to get the solubility homework done, okay? So, are there any other questions before I move on to the next topic, which actually is the topic that he raised? Okay, great. So in the homework that's due tomorrow, there are lots of examples of solubility product and common ion effect that I would like you to work out. Now we're actually ready to move on to the next topic, which is looking at electrochemistry. So we're going to look at chapter 13. And we're going to look at electrochemistry. All right? Now, electrochemistry deals with oxidation, reduction, reactions. All right? So when we start look at electrochemistry in detail, we need to understand, before we start looking at electrochemistry, we need to understand what it means when we say it's an oxidation-reduction reactions. Many of you may have seen this in high school already, but it turns out if you take all the reactions that are known, virtually all of the reactions that we know to date, it turns out these reactions can be placed in 3 categories. All right? So all chemical reactions can be categorized into 3 classes of reactions. The first class of reactions are called acid-base reactions. And as all of you know, acid-base reactions involve proton transfer. So you know that when you deal with acid-base reactions, you have an acid, which is the proton donor. You have a base, which is the proton acceptor. And when an acid reacts with a base, essentially what happens is a proton is transferred from one to the other, and we call them proton transfer reactions. So what you have to be able to do is look at the 2 reactants. And in that, if you look at the reactants and look at the products and you see that there's a proton being transferred, then you know it has to be an acid-base reaction. All right? If one reactant, a proton is transferred from the one reactant to another, you know that's an acid-base reaction. The second class of reactions are the ones that we've looked at also, and these are called precipitation reactions. All right? These involve the formation of precipitates. And so we said if you take two substances that are completely soluble and combine them and you end up with something that's insoluble, we call that a precipitation reaction. So the second class of reactions are where you start with reactants that are completely soluble and you combine them and you end up with something that's insoluble. Okay? And how do you know whether something is soluble or insoluble? You have to keep the solubility rules handy with you as you look at it to figure it out. Okay? The third class of reactions are the oxidation-reduction reactions, and that's what we're going to look at today. So the third class of reactions are called oxidation-reduction reactions, and these involve electron transfer. All right? So when you deal with oxidation-reduction reactions, what you are looking at is electrons being transferred from one substance to another. So one substance gives off electrons, and we call that the electron donor. And the other substance picks up the electrons, and that's the electron acceptor. And the end result is that electrons are being transferred. It turns out virtually all the known chemical reactions can be placed in any one of these categories. All right? And the one that has the most abundant examples, the majority of the reactions actually fall in the latter category. So the majority of reactions are actually oxidation-reduction reactions. So we're going to look at the third class of reactions. And we're going to look at some very fundamental background stuff that you need to know about oxidation-reduction reactions before we actually start looking at electrochemistry itself. So we're going to start looking at oxidation-reduction reactions. And we're going to look at oxidation-reduction reactions. And we're going to start by looking at some basic definitions. All right? So the first thing is that these reactions involve transfer of electrons. All right? And so because they involve transfer of electrons, we're going to define some terms. You're going to start by saying oxidation. This is the chemical substance that loses electrons is called let's say, let me rephrase this. This doesn't sound very good. So the chemical reaction in which a substance loses electrons is called oxidation. All right? So if you want to redefine this, let me write that clearer so you can see it. Okay? So if I want to say oxidation, the chemical reaction in which a substance loses electrons is called oxidation. All right? And the second part is reduction. So a reduction would be the chemical reaction in which a substance gains electrons is called a reduction. All right? Now, this is very similar to acid-base chemistry. Remember, we said acid-base chemistry involves proton transfer. So one substance loses electrons, and that substance is called the acid. The other substance picks up the protons, we call that the base, and when the proton gets transferred from the acid to the base, we end up with an acid-base reaction. Likewise, when you deal with oxidation-reduction reactions, one substance gives off one or more electrons, all right? And when electrons are given off, we call that oxidation. So oxidation is electron loss. When the process involves loss of electrons, it's oxidation. So just like, remember we said an acid is a proton donor, a base is a proton acceptor. Here we say oxidation is electron loss, reduction is electron gain. Okay, so reduction is electron gain. All right? Now the substance that loses electrons, all right? In other words, the one undergoing oxidation is called the reducing agent, and the substance that gains electrons, in other words, the one undergoing reduction, is called the oxidizing agent. All right? So these are terms that I want you to be familiar with. So oxidation-reduction reactions involve electron transfer. So one reactant will give off electrons. If it loses electrons, we call it oxidation. The other substance will pick up electrons. And if it picks up electrons, then we say it's undergoing reduction. And the substance that undergoes oxidation is called the reducing agent. It undergoes oxidation, but it is the agent that's responsible for reducing the other. Do you understand that? So the one that's undergoing oxidation is the reducing agent, and the one that's undergoing the reduction, because this is the one that's undergoing reduction, but it is the one that's responsible for the other one undergoing oxidation. Do you understand? If this is undergoing reduction, it's the other one that's being oxidized, all right? And so this is the agent that oxidizes the other. So if it's undergoing reduction, then it is the oxidizing agent, okay? Now what you want to keep in mind is just like proton transfer, you have to have a substance giving off protons and you have to have another substance picking it up. That's how you can have proton transfer. Likewise, when you have oxidation-reduction reactions, you have to have both of them together. You have to have one substance giving off electrons. That's the oxidation. But you have to have another substance there to pick up the electrons. Do you see that? So oxidation and reduction go hand in hand. You can't have them separately. You have to have one substance giving off electrons, and you have to have the other substance picking up electrons. Now the problem is, with acid-base reactions, it's easy to look at the formulas and say, oh, this is missing one proton. This has picked up a proton. So you can look at it and say, oh, this is the acid, this is the base. Unfortunately, with oxidation-reduction reactions, when we write balanced equations, do you have electrons there? No. So when you see oxidation-reduction reactions, it's not directly apparent whether electrons are being transferred, whether one substance is losing electrons and another substance is picking up electrons. All right? So in order to figure out whether electrons are being lost or gained, or who's losing electrons, who's picking up electrons, we have a set of rules that we use. And this is called rules for assigning oxidation numbers. So we have this system of rules for keeping track of electrons. So we want to figure out how many electrons did it start with, and how many electrons does it end up with? Is it losing electrons, or is it gaining electrons? So For the next class, I have on the class website, I've put the rules for assigning oxidation numbers. And at the beginning of class, we go through some exercises where we go through figuring out whether something is losing electrons or gaining electrons. All right? So let's stop there for today.